back to the one more session of multimedia systems. So in the sessions we will be continuing with the topic of optical storage media. Let us recall with the previous session. In the previous session we had discussed about the introduction about the optical storage, the detailed history of the optical storage, the basic technology, how the optical storage works, what are the principles involved, and we have also seen about the video disk and the WORMs, that is write once readable memories, and we have also seen the various properties of the worms, that is write once optical storage devices. Let us continue with one more technique, that is compact disc digital audio. This is also represented as CDDA. Okay, as the name itself suggests, this compact disc DA, that is this technology was jointly developed by NV Philips and the Sony Corporation. See, we know that most of the technology has been developed with the combination of NV Philips and the Sony Corporation. What was the main intention? Here, the main intention was to store the audio data, but the basic technology was totally understood and developed by NV Philips, and it was contributed by the Sony Corporation in order to come into existence. When we talk about the technical aspects or the technical basics of CDDA, let us look into it. What does it have? This CDDA is with a diameter of 12 centimeters. Which is common with respect to the previous CD technology also, and this is played with the concept of constant linear velocity. We call it as CLV. Means we know that audio needs to be in continuity. I told you in the previous session what happens if there is a discrete, means how a discontinuity is there. Means we can see that the problem that we encounter in a telephone, if there is no continuous video media, we get irritated. We feel that there is a no connectivity continuous thing. We try to disconnect the call here in the telephone itself. Means we need to have a continuous flow of information, that is audio. In the similar way, in order to have a complete flow of audio without any obstacles or intervention, this CLV, that is constant linear velocity technique, was deployed in the CDDA technology, and the number of rotations per time unit depends upon totally the radius that is been currently sampled with respect to the CDDA. And we have seen that the spiral winding, I have already discussed about this at the beginning session itself. This is the spindle, okay, where the center portion of the CD. So the tracks and the sectors will be in the spiral shape kind of thing. Now here this CDDA have an approximately 20,000 windings. This is a much more greater things. It has more than the other technologies comparatively that was in existence. Means it has 20,000 windings with almost compared to the 850 windings that we have encountered in the previous session, that is long play. When we talk about the long play, it has only 850 windings. What is long play? We have seen in the beginning when we talk about the history of the CDs, we have seen that in the history of the CDs, the long play has only 850 windings, whereas the CDD has 20,000 windings, which is far more better than the existing one. When we talk about a 20,000 winding, there could be a continuous audio data streams present. Now the length of the pit is always in the multiple of 0.3 micrometer. Means each pit is represented to store the data. Now the pit size would be 0.3 meter. The change in the pit to land or the land to pit is coded by the 1, means the binary bit 1. It indicates there is a change. If there is no change, there would be no binary bit 1, means a 0 will be prevailed continuously. We will represent it and see it. Now we have seen this. We know that the typical CDDA or a CD technology consists of pits and lands. Now let us look into the diagram where this protuberance is said to be a pit. Okay, and this portion is said to be a land. Now when we consider the partition, this would be the substrate layer. Okay, and before this protective this, there would be one more layer called label. Now this would be a substrate layer. Now while representing this portion, see, look at this. This is the mark of the land and this is the area of the pit, again the land. Now when we want to represent the combination of pits and land, here we will neglect this part, we will start here. Here the land is starting, so it starts with 1 and some combination of zeros. Again after the land, what is that? A pit is starting, so it is changing the state. Again it is followed by some amount of bits. Again from pit to a land is changing, so 1 and some combination of zeros. The combination of zeros depends upon the size of the thing. Now when we talk about the size of the pit is 0.3, means here when we talk about this, this is about 0.3 micrometers. This is what we are talking here in the previous session. So this makes the continuous, that is CLV, constant linear velocity, is achieved. Now when we know about the working principle or the basic technology of the CD, let us look into the audio data rate of a CDDA. Audio data rate. What do you mean by audio data rate? A audio data rate can be easily derived from a given sampling rate. Means if a sampling rate is given, the rate of audio that is being transmitted is said to be the audio data rate. How does we calculate it? So when we want to calculate, there should be a predefined data. So what are those predefined data? We need to know the sampling rate. In the previous session itself, we have seen what is the sampling rate of a CD technology. That is, sampling rate is said to be 44,100 Hz. So this is said to be the sampling rate, and when we talk about the sampling rate, we need to have one more thing: at what rate the sampling has been done, that is the quantization. Here the linear quantization is happening. Either it should be 8-bit quantization or it should be 16-bit quantization. Here we are considering about the 16-bit quantization. That is what kind of quantization? That is linear quantization. Now we have the frequency of the sampling rate, we have the quantization, then we are using the stereo type of audio signals. When we talk about the mono, it is single channel. When we talk about the stereo, it is said to be 2 channels. So we need to know that. So stereo means we have 2 channels. Now we have all the data. When we have all the data, we can now calculate the audio data rate. It states that 16 bit, what is that 16? 16 bit is the linear quantization, means at this time we have 16 bit of sample value. We can have 16 bit of sample value into how many channels we have. Since we are using stereo, we have 2 channels. Into what is that we are doing? We are having a sampling. What is the sample value per thing? What is the sample value we have already given? The 44,100 hertz. Hundreds of samples. By what is that? Each channel has into separate of S channels. Now, when we use this equation, we would be almost able to get the value of 1411,200 bits per second. But we always talk in the form of kbs, that is approximately is equal to 173 kbs, that is kilobytes per second. Now this is said to be 173 is said to be the audio data rate, means the rate at which the data has been transmitted from one or source to destination, or which has been sent from the device, is the 173 kilobytes per second. We call this as audio data rates. Now when we know about the audio data rates, we can also calculate the signal to noise ratio. Means what do you mean by signal to noise ratio? Means the tolerance, means or the tolerable things that can be achieved with the CDDA. Analog long play records or the cassette tapes have a signal to noise ratio of 50 decibels. Let us look into this signal to noise ratio also. So when we talk about the long play or the cassette, signal to noise ratio is achieved to 50 to 60. That's all. What 50 to 60? It is decibels. Now let us talk about what is the signal to noise ratio when compared to CDDA. Obviously, when you have 2000 windings, while we had a signal to noise ratio of with respect to CD or a long play, it's 50 to 60 with the 870 windings. Now with the CDDA of 20,000 winding, obviously there should be a more possibility to handle. So given the 16-bit linear quantization, yes, we are always using 16-bit of linear quantization. Now what we are doing, signal to noise ratio of CDDA. Yes, signal to noise ratio of CDDA can be represented as by how many bits? When we talk about the standardization, we use 6 bit of 6 decibels are permitted. 6 decibels per bit means the permissible bit of signal to noise ratio is obviously default one is a 6 bit into how many bits we are transmitting, into 16 bits, because we are using 16-bit linear quantization. That would give you about 96 decibels. So, this is about the practicality with respect to equation. So, when we talk about the signal to noise ratio of CDDA is almost 96 decibel, whereas with respect to the cassette tapes and CD long play, we are able to achieve only 50 to 60 decibels. So, here also the signal to noise ratio is much more compared to the previous technology. The audio data rate has been increased, the signal to noise ratio has also been increased. When both the things have been increased, let us look into the capacity that can be achieved in a CDDA. Now, let us look into the capacity. The play time of a CDDA is at least 74 minutes. So, these data are very much needed in order to support the equations. Means we have 74 minutes. Using this value, the capacity of a CDDA can be totally determined with respect to audio. Here we are only talking with respect to audio concept, not other than any concept, because we are talking with respect to CD digital audio, that is CDDA. Now let us look into the capacity, that is capacity of CDDA can be determined by the equation, that is how many minutes are possible in a CD, that is 74 minutes into, next is what we have seen the audio data rate. What is the audio data rate? That is 1411 into 200 bits per second. We have already derived the audio data rate. So, when we have these two things, we have the huge number. It is very difficult to remember. So, I am looking into it and writing, that is 6 into 265 and 728 000 bits. See, this amount of bits can be accommodated. When we convert this bit into MB, because we know that CD, when we convert this CD into, always we represent the capacity of CD in KBs or MB, because it's a much more bigger quantity. We try to convert this bits into MB, we get an approximation of 747 megabytes of information. Means the capacity of CDDA is almost 747 megabits. So, we have seen about the data rate, signal to noise ratio and the capacity of the CDDA. Let us look into the one more concept, that is 8 to 14 modulation. So, all these terminologies, that modulation, 8-bit modulation, 16-bit modulation, quantization with respect to linear and non-linear, all these terminologies we have discussed in the beginning session itself. So, now it would be very much easy for us to continue. Now, when we talk about this 8 to 14-bit modulation, what is this? The change of bit to land or land to bit is represented by the starting bit 1. We have seen that in the representation just now. So, if there is no change in the correspondence with the bit to land or land to bit, it is sustained with a 0 itself. Means any change is represented by 1. So, when the bit to land is very close, So it is represented in a such a way 101010. Again it's a problem. And second case, if the bit to land, that is the bits are represented in a very larger way, means change of bit to land is very long. So 1 0 0 0 0 4 and it takes place with a longer duration, and then there is a one more change or from bit to land or a land to bit. So then it will again a problem. Why? What is that problem? We see that. So on the other hand, the bits and the lands cannot be too long, because the synchronization signal, that is a clock signal, cannot be determined properly, because in the two cases the clock signals causes problem. One, if the bit land is too close, it happens like this 1 0 0 1 1 1 1 0 1 0. So it is obviously very difficult to understand the data itself, because there is a immediate change of shift. Second case, if the bit to land shifting is too long, again the problem is there. So in order to overcome this problem, the maximum length of bit and the land, thus it was limited to at most 10 consecutive zeros, means there should be at least 10 consecutive zeros, then there could be a change of shift, or with respect to change of clock can be permitted or triggered. So this was achieved by 8 to 14 bit modulation. Let us look into the pictorial representation. When we talk about 8 to 14 bit modulation, so the 8 bit was converted into 14 bit modulations, because there were more possibility of representing these bit and lands in a conventional way, so that we are able to allow a maximum distance, that is 267 values were permitted. 267 values, of which 256 was completely made use. Now let us look into it. So audio, bits, I'll show you with just one example, then the modulated bit. Now let us consider a simple 8-bit modulation where it consists of all zeros. Now how to represent this in a 14-bit modulation? So in a 14-bit modulation, it can be represented as and one more zeros. Yes. Now what has happened here? See here, in this case, there is no change or phase shift or with respect to clock triggering pulse itself. Now here the phase shift can be achieved at the regular intervals, and also the representation is made smooth, means more number of data can also be accommodated, and change of shift is also triggered with respect to clock pulse. But here it is not possible, so it is very difficult to analyze these kind of things. So these were the implementation which was done with respect to the 8 to 14 bit quantization. Then we look into the one more concept called error handling. What is error handling? Obviously it's simple. The goal of error handling on a CDDA is to detect and correct the typical error patterns. No, you might be seeing that. Does CD also consist errors? Yes, in the beginning itself I have considered. I told you about this problem. So it would be only with respect to mismatch or the scratches or some kind of dust that can be causing with respect to errors. Moreover, it is an interleaved architecture, so errors would be very less negligible, but still we need to take care of the action that needs to be taken with respect to detect those errors and correct those errors. So errors are usually the result of scratch or dust. It is very clear. So error handling can be done in two ways. The first one, that the first level of error handling implements two stages. In the first stage itself, there are two things. One is we use the Reed-Solomon algorithm. What does we do here? So what does the Reed-Solomon algorithm does? For every 24 bytes, okay, it is classified into two. Means look at this, Reed-Solomon algorithm does for every 24 bytes of information, it classifies into two. So what are two groups? First one is correction of data bits. So when we talk about correction of data bytes, each 4 bytes means this side 4 bytes is there and this side is 4 bytes. What is that? This is called the correction of data bytes. The first group corrects only single byte errors. Look at this. This is group 1 and this is group 2. So both are for correction of data bytes. The first group corrects only single byte errors. This group, which consists of 4 bytes of information, corrects only the single byte error, whereas the second group corrects double byte group's error. Make it clear? So error handling is classified into two categories, that is two levels. At the first level itself, we use the Reed-Solomon algorithm. What does the Reed-Solomon algorithm does? For every 24 bytes of what kind of bytes? This is audio. You should remember always we are talking about only CDDA. So every CDDA with respect to 24 bytes, the Reed-Solomon algorithm classifies into two groups of 4 bytes each. Group 1 only corrects or checks for the 1 byte error, that is single byte error, and the second group corrects only for 2 or a double byte errors. This is with respect to first level. So what happens in the second level? In the second level, the real consecutive data bytes are distributed over multiple frames. Means now here in the first level the things are corrected. In the second level it is distributed over the multiple lines. The audio data are stored interleaved. This has to be remembered. So when we talk about the distribution, here the interleaved property appears. When we talk about interleaved, between the tracks, so the CDDA, so that the burst errors will always damage only the parts of the data, means not completely. So there would be tracks. So in between the interleaved space, the data will be stored. So if there is a scratch or any tamper or a dust, only some portion of the data is damaged, not completely. So using this technique, we can get the error handling rate of 10 to the power of -8 is achieved. And this is called the error handling. So this is the most advantageous of the CDDA. Then when we talk about the error handling, then let us look into the advantages of the CDDA. So advantages finally. So if there is a lot of properties, that is audio data rate is good, signal to noise ratio is good, capacity is good. We are using 8 to 14 bit of modulation, the modulation is also good, and we have also seen the error and handling is also much more good than what are the advantages. Let us look into that. The errors can be caused only by the damage or dust. This is the main property of CDDA. Then for uncompressed data, CDDA is very insensitive. So because it is not compressed, so slight damage is not at all affecting the data quality. So it is aram, so it can work up with those things. And after a long period of time of digital technology, CDDA would be very identical and there is no mechanical wear and tear. It can be used as long as then we might have seen with when we talk about the machineries, over a period of time there would happening a cause of wear and tear with respect to damage, whereas here it is no such kind of things, wear and tear. Only thing is the minor scratches. So though it is those scratches occur, it is not causing much damage because we are using interleaved, and I am talking about the uncompressed data because your data is free. So when damage happens, it is not happening for more sort of data, it is happening only for the portion of the data. And the specification here is 8 to 14 bit modulation, it is an upper hand. And second, the cross interleaved read solve algorithm or a code is always used. This helps the CDDA to detect the error and also correct the errors, and it provides compatibility across the various systems. These are the very much advantages with respect to CDDA. So these were the topics. Okay, we'll look into the summarization of this session. So in this session we have discussed starting from the compact stick digital audio, we have seen the technical basics, the complete things with respect to CDDA property, and we have seen the audio capacity, that is audio data rate. When we talk about the audio data, it is a rate at which the audio can be transmitted. We have a very good audio data rate, and we have seen the capacity, that is 747 MB compared to whereas the other long plate is much more higher, and this CDDA is also using the technique of 8 to 14 bit modulation. When we have 8 to 14 bit modulation, it is much more efficient in representing the data. And when we come to the concept of error handling, yes, the fantastic read solve algorithm incorporates the complete technique of error detection and correction. When you have all these things, there are a lot of advantages with respect to CDDA. So these were the topics I had wished to discuss in this session. Thank you very much.